Welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In this video, we'll evaluate the performance of a single P-100 GPU on the ACCell nodes. We'll measure its efficiency in matrix multiplication, presented in Giga-Flops per second, utilizing OpenACC directives. You can access valuable insights about OpenACC on the Nvidia website. Let's navigate to the OpenACC pages to find more information. As we scroll through the documentation pages on OpenACC, we encounter a list of environment variables. We'll utilize the NV compiler ACC time variable to monitor GPU performance. I've developed a Fortran program for GPU offloading using OpenACC. It's important to note that we need to incorporate the OpenACC module. Just like in our previous video, we'll begin with the matrix dimension n set to 16,384. In the nested loop for matrix multiplication, we've integrated one OpenACC directive. A comment sign followed by a $sign and the letters ACC marks this directive. In this instance, we're using the kernel's directive, which is the simplest method of offloading. Essentially, it allows the compiler to determine the optimal offloading method. We'll save this program with the file ending set to 1. It's worth noting that this program retains the original loop sequence with I, J, and K. In a separate Fortran program saved with the file ending 2, we've implemented loop interchange similar to what the Intel Fortran compiler utilized. Consequently, the loop sequence is now arranged as JK and I. In another Fortran program, labeled with file ending 3, we've maintained the same loop interchange as before and introduced the OpenACC directive data. This directive offers various options, including copy in, copy out, and copy. Here, we're utilizing the copy-in option to transfer matrices A and B from the host to the device. Matrix C, on the other hand, is initially copied from the host to the device, and then from the device to the host. It's important to note that matrices A and B are not copied back to the host from the device. In the last Fortran program, we're using the intrinsic function matmul to execute the matrix multiplication. This program will be saved with the file ending 4. We will be using OpenACC on the ACCell compute nodes, and this must be specified in the testing Python script. Additionally, we need to select the OpenACC offloading method to ensure that the correct compilation options are used. We have introduced the Fortran programs we'll be using, which are numbered from 1 to 4. We'll start with the first one. Monitoring is disabled, as we will utilize the NV compiler ACC time environmental setting to track GPU performance. The value of n must be set to 16,384 to obtain accurate performance measurements, and we will execute the tests only once. From our previous videos, we know that the billing factor on the ACCell nodes is 6, which is used to calculate CPU time consumption. We utilize our setup Python script to request 1 GPU on the ACCell nodes and 7 GB of memory, given that n equals 16,384. We use our NVHPC alias to load the latest NV Fortran compiler and set the environment variable NV compiler ACC time equal to 1. By configuring this environment variable, timing data for accelerator kernels will be presented in your terminal upon execution. Then, we execute our setup script and confirm via our CPU bill alias that the billing factor remains at 6. We're starting our testing with the Fortran program, designated with file ending 1, maintaining the original loop sequence of I, J, and K. The testing Python script has adjusted the compilation command. Specifically, the minfo option is added to gain insights into the compiler's actions. Additionally, we're utilizing the ACC compiler option. Upon examination, we observe that the compiler has executed a copy of matrix C and implemented a copy in operation for matrices A and B. It's important to highlight that the compiler fails to parallelize the innermost loop at line 28, which corresponds to the K loop in the Fortran program. This inability to parallelize the loop means it will be executed sequentially, potentially impacting performance. As we demonstrated in our Fortran optimization video, vectorizing the innermost loop is essential for enhancing performance. The compiler successfully parallelizes the two outermost loops in the program, namely the I and J loops. It's noteworthy that the compiler opts to collapse these two loops into one and implement a loop gang parallelization strategy. Further discussion on loop gang parallelization will be covered in our upcoming videos. The OpenACC environmental variable NV compiler ACC time offers valuable insights into accelerator kernel timing. It indicates that the kernel was initiated once, taking approximately 61 seconds to execute. For data transfers, the copy-in operations for matrices A, B, and C collectively consumed about 526 milliseconds, while the copy-out operation for matrix C required around 166 milliseconds. Matrices A and B are transferred from the host to the device, while matrix C undergoes a two-way transfer, first to the device and then back to the host. Notably, in this scenario, data transfer doesn't significantly impact computation time. The wall time for this test is roughly 66 seconds, resulting in a performance of 22 Giga-Flops per second based on CPU time. These metrics closely resemble those obtained with the do concurrent method in our previous video. Using our testing Python script, we can assess the Fortran program with the loop interchange, denoted by the file ending 2. We can see that the compiler has optimized its parallelization approach, now employing loop gang on both the outermost J loop and the innermost I loop. It's vital for performance that the innermost loop is parallelized and vectorized, allowing efficient utilization of the core's vector register. The copy-in and copy operations follow the same pattern as the previous test. The accelerator kernel timing data reveals that the kernel was launched once, lasting approximately 33 seconds. The durations for the data transfers remain consistent with previous tests, approximately 526 milliseconds for copy-in and 166 milliseconds for copy-out. The wall time for the test is about 37 seconds, with a performance of about 39 Giga-Flops per second. These numbers closely resemble those obtained with the do concurrent method. When examining the Fortran program with file ending 3, which incorporates data transfer directives, we noticed comparable behavior to the previous program. This is because the compiler performed the same type of data transfer even without the explicit data directives. Furthermore, the compiler continued to apply loop gang parallelization on 2 loops. The accelerator kernel time indicates that the data region was accessed twice, corresponding to the directives we specified for data transfer. The duration for the data transfer remains consistent at 526 milliseconds and 166 milliseconds, as observed previously. The wall time for this test matches that of the previous one at about 37 seconds. When we attempt to execute the Fortran program with file ending 4, which utilizes the intrinsic function matmul for matrix multiplication, we notice that the compiler does not parallelize the code. Instead, it generates a serial kernel. The compiler is unable to parallelize this intrinsic function. To conclude this test promptly, we will use the Ctrl-Z command followed by exit, as the execution is expected to be time-consuming. We also utilize the exit command to log out of the interactive Accel node C78. It's unfortunate that the compiler couldn't parallelize the intrinsic function matmul. What would the performance be on the A100 nodes? We'll explore this in our next video. I am looking forward to the next video, wishing you all happy computing in the meantime.